Hello. A very warm good evening to all of you. Welcome to the seventh lecture of this series on solar system, proudly hosted by Physical Sciences Consultorium with its science outreach partner, Science for Everyone. Physical Sciences Consultorium is founded with the twin vision of taking frontier scientific knowledge among the masses and fire the interest of youths in science. As a remarkable milestone of this lecture series, we are talking about techniques and application of planetary radar astronomy. During an era when spacecraft observations have produced a great majority of new information about our solar system, observations of solar system bodies from the Earth using high-powered radar system have produced some remarkable results. Some of these include the discovery of condensed volatiles, most likely water ice, at the poles of Mercury, first ever surface views of Venus, high resolution imaging of main belt and near Earth asteroids, multi wavelength measurement of the scattering properties of the icy Galilean satellites of Jupiter. So, for this, we have invited a very special guest for this very discussion. And we have Dr. Sriram Saran live with us from Ahmedabad. Thank you. Thank you so much for being with us. We have Dr. Sriram Saran live from Ahmedabad with us. It is a great pleasure for me to introduce you on this platform.
Yeah, can you hear me?
Sure. I can hear you properly. So, for this, it is a great pleasure for me to introduce you on this platform. Dr. Sriram Saran received his MSc degree in physics from Nagarjuna University, Andhra Pradesh, and MTech degree in geomatics from Jawaharlal Nehru Technological University, Hyderabad in 2004 and 2006, respectively, and a PhD degree in physics from Gujarat University in 2016. From 2010 to 2016, he worked as a junior research fellow, followed by a research associate at Space Application Center, ISRO, Ahmedabad, where he was involved in polarimetric radar studies of the moon using orbital-based radar datasets. From the year 2017 to 2018, he worked as a postdoctoral research scientist with the Planetary Radar Group at Arecibo Observatory, Puerto Rico, where he was involved in the radar observations of near-Earth asteroids, comets, and moon. From the year 2018 to 2020, he was a postdoctoral fellow with Lunar and Planetary Institute, Houston, where he was involved in polarimetric radar studies of terrestrial planets and asteroids, along with laboratory simulation studies to investigating planetary radar scattering process. Currently, he is back with the Space Application Center, ISRO Ahmedabad, as a staff scientist for in the planetary science group working on Chandrayaan 2 mission. I feel privileged to know him as a compassionate human being and a committed scientist who is up for a better society. Sriram, I'm truly delighted to have you here. Thank you so much for taking precious time for us from a busy schedule. I'm inviting you for your presentation to this gathering. Please take over.
Thank you, Lalit, for your brief introduction. Can you hear my voice?
Yeah, I can hear you. You
Okay.
can say presentation.
Okay, I have targeted like 40 to 45 minutes for my talk today. So let me share the screen.
Yeah. Yes,
Okay, can you
this
see the screen?
yeah, I can see. You can put it in presentation mode, and then yeah,
Yeah.
it is perfect.
Okay.
So we can start.
Yeah. Okay. So from the past 7 to 8 decades, we have gathered so much information, and so we have unraveled so many mysteries of our solar system using mostly remote sensing techniques, both from spacecraft-based uh, data as well as data collected from the Earth. So today I will be concentrating on how do we collect such remote sensing data from the Earth-based observatories, that too in particular radar observatories. We have so many observatories across the globe that operate at radio wavelengths, which is basically once to 100 centimeter, typical of radar remote sensing studies. So the screen shows the world's largest planetary radar facility on Earth, which is located at Arecibo municipality of the Puerto Rican island, which is a part of USA. I will show today some uh, brief introduction to the planetary radar astronomy, followed by the technique we use, which is the delay-Doppler mapping technique, and some significant results from Arecibo Planetary Radar, because that's where I have worked as a postdoc a couple of years ago. And then I will summarize. So the planetary radar studies from Earth have been undertaken by scientists since the 60s. So it will be impossible for me to show all the results in a comprehensive way in such a small time, but so that's why I have put very significant results from the uh, Arecibo planetary radar system. So why do we call this as planetary radar astronomy is because this is an intersection between two fields, that is the planetary science and uh, radio astronomy. Because typically we use the radio astronomy observatory facilities such as the Arecibo and Green Bank Telescope in Virginia, and we add uh, radar capability to those observatories in order to study the planetary bodies of our solar system. Now, this has proved to be a very powerful technique, which can give us very complementary information that is unavailable from other parts of the wavelength, such as optical and thermal infrared observations. Now, there are some great advantages in this planetary radar astronomy, because the observer's control of all the attributes of the signal we use. That means an observer who does the planetary radar observations will have total control on what he's doing, what he or she is doing. So the observer can control the signal in terms of its wavelength, frequency, in terms of its polarization. So, so polarization is a very fundamental aspect of this technique we use. We all know that polarization is a inherent property of electromagnetic wave. We can control the transmitted and received polarization, study them to glean information on the target. The second important advantage is that, so basically we transmit power at radar wavelengths into the space, and when it gets received back from the object, we resolve that power into uh, two different directions, or you can say two different domains. So we distribute that power into time delay and Doppler frequency, which I will be talking about a bit more detail in the following slides. So typically radar observations employ centimeter to meter wavelengths, which is complementary to optical and thermal infrared observations, which operate typically in microns. So these centimeter to meter wavelength signals from the radar, so they penetrate some optically opaque. Hello. So they can penetrate some optically opaque media like the clouds, planetary clouds. For example, Venus and the Saturn's moon Titan have large amounts of clouds, which make optical observations of those planetary bodies impossible to see what's beneath the clouds. But radar can penetrate those kind of optically opaque media, and also the coma of comets. So when you see a comet, you know that it will have a center nucleus and will have a long tail as it approaches the sun. So radar can penetrate through the comet because it is made up of dust and gas and rocky bodies. So this kind of observations permit the study of near surface physical structure and several other physical properties such as bulk density, and then composition to some extent, and they are highly sensitive to the presence of metals and also ice. I will show some examples for all these parameters I have discussed now. So these are the three main advantages of radar in typical planetary observations. Now we have several radar systems across the world, but in terms of the sensitivity and the number of objects that can be observed in the solar system, there are three dominant planetary radar systems currently in operation. Even though we have other observatories like Evapatoria in Crimea and Hicamarca in Peru, but these three on this slide, which is the Arecibo in Puerto Rico and the Goldstone DSS-14 antenna, this is operated by Jet Propulsion Laboratory of NASA. This is situated in California. And the third one on the bottom is the Green Bank telescope, which is situated in West Virginia. So the above two radar systems can both transmit radar waves and receive radar waves, while the Green Bank telescope on the bottom can only receive radar waves. It cannot transmit radar waves into space. So the Arecibo is the world's largest radar system. Its dish, which you can see here, it's a 305-meter dish, which is fixed to a sinkhole into the ground. While this Goldstone system on the right, this is a 70-meter dish. It can rotate 360 degrees and can point object into the sky. Whereas the Green Bank telescope is the world's largest fully steerable radio telescope. So it has an aperture, this dish diameter of 100 meters. So the most important criterion to observe a solar system object from the ground-based observations is the signal-to-noise ratio. That means how much signal you have when you compare with the noise that is inherent with the radar systems. So the signal-to-noise ratio, it is the ratio of this received echo power to the root mean square of the receiver noise. Now, this is expressed as a factor of both the system factor and the target factor. So, system is our radar system, which we use for transmitting and receiving. The target factor is a function of the planetary body under observation. Now, if you see all of them, the most important parameter here is the this distance. So how much distance a target is from the Earth? This is a very important factor in conducting these observations from the planetary radar facilities. So the inverse fourth power dependence of this signal to noise ratio on the target distance, that means if so R is the distance from, let's suppose Mercury or Venus from Earth. Now, the more distant it is, the very less amount of power we receive from the ground, because the SNR is inversely proportional to the fourth power of its distance from the Earth. So this severe limitation can be overcome by constructing these huge, powerful, sensitive telescopes such as the Arecibo and Goldstone. That's why we need very huge collecting dish antennas. So Arecibo, as I've told before, it's a 305-meter dish, whereas Goldstone, it has a collecting surface of 70 meters, and Green Bank has 100 meters. That's why you need very huge collecting areas in order to get the required sensitivity after the signal bounces back from the planet. Now, if you compare these two planetary radar facilities, Arecibo versus Goldstone, both have complementary abilities. So you can see that apart from the diameter, the Arecibo can use typically two frequencies. So in radar remote sensing, we have several observation bands. That means frequency bands in which we observe. So 2380 corresponds to around 13 centimeter wavelength, whereas 430 megahertz corresponds to 70 centimeter wavelength. And so these two are the operational wavelengths for Arecibo, while Goldstone system, it operates in X band, which translates to around 3 centimeter wavelength. So Arecibo can pump up to 1 megawatts of power into the space. This is like huge. You need to produce 1 megawatt of power from the ground, and then you need to pump it into the space in order to illuminate the target. Whereas Goldstone can typically pump up to half of what Arecibo can illuminate. That means around 500 kilowatts. Now, another important distinction is the declination coverage. That means how much sky can the planetary radar facilities scan, because these are fixed into the ground. Because they are not fixed onto a spacecraft, so they can only see very limited sky coverage. This declination coverage, it enforces a kind of limitation of how much sky you can see from the ground. So for Arecibo, 38-degree declination means it can only see up to 20 degrees of its zenith. That means 20 degrees exactly to the north of the telescope. Whereas Goldstone can see a very large range of the sky because it can rotate on its axis. So this translates to around 1/3 of the sky coverage from the Arecibo radar, whereas Goldstone can see 80% of the sky. These are the resolutions possible from both these systems. And another important distinction is the tracking time. So because Arecibo is fixed into the ground, the dish cannot move. That means the primary collecting surface cannot move. There is a tracking system which is fixed on top of the antenna, on top of the dish. So it can only track up to 22.6 hours per day, whereas the Goldstone can operate 24 hours throughout the day. So to summarize, Arecibo is around 20 times more sensitive than the Goldstone system, and so it can detect solar system bodies to about double the distance of what we observe from Goldstone. So some of these features of this telescope are, so since the dish cannot move, you need to have some kind of setup through which we can target any solar system object. So on top of the dish, you have this huge azimuth arm uh, onto which this dome is connected. So typically, this dome consists of the transmitters from which we illuminate the targets. So to point to any object, this azimuth arm rotates, like for example, into the screen, and then from here uh, towards outward the screen. That means it can rotate 360 degrees, whereas this Gregorian dome can move from left to right. So in this way, we can illuminate the targets. So yeah, I have, as I have said earlier, these are the pointing restrictions for the telescope. So it can only track up to a maximum of 2.6 hours per day. So let's start with the basics. How do we do this kind of observations? So as you can see, we transmit a signal from this dome. It gets onto this dish, gets reflected here, and then travels to an object such as Mars, as I have shown here. And then from Mars, it reflects back and it reaches the dish. And from the dish, it again goes back to this dome in where the receivers are located. So in this way, we transmit the signal and then wait for some time. So the time depends on the round trip light time. That means how much time the signal takes from the Earth to that object is called the distance. And round trip time is twice of that time. So we wait for the signal to receive. It gets bounced off from this huge dish, and then it gets collected into the receiver here. So the red lines depict the transmitted waves, while the blue corresponds to the received waves. So sometimes we use a different configuration, which we call as the bistatic setup. That means we transmit from one observatory, such as Arecibo. So the wave goes back to an object, such as Mars or Venus, and then we collect the incoming signal at some other observatory. So in this example, I have shown that while we transmit from Arecibo, uh, it is being collected at Green Bank. So this has some advantages because for close objects such as Moon and Venus, the round trip light time is very less. So typically the change time between uh, the transmitter and receiver at Arecibo is around 7 seconds. So for example, the round trip light time for Moon is 2.5 seconds. That means if you transmit a wave from Earth, it goes back to the Moon and comes back to you. So this time is around 2.5 seconds. So because Arecibo takes around 7 seconds for switching from transmitting to receiving, you cannot observe this signal from the Moon because it is very much shorter than this switching time. So that's why we need a setup called bistatic setup. So we take help of these observatories situated elsewhere, such as Green Bank and sometimes at Goldstone. So after we transmit, what do we receive? Now, any changes are due to the object under consideration. Now, the received signal is very weak. It is around 10 to the power of minus 27 of transmitted signal power. So that's why we need such huge sensitivity of the received signal. In order to receive such a very, very weak signal, you need to have a very huge collecting dish so that it can focus all this energy back to the receiver. Now, after we receive the signal, it goes through various processes, such as it is mixed with the baseband frequency, and then we filter it. we attenuate some part of it, and then we amplify it, so that the received voltage is recorded as a function of time. So basically what we do is we transmit power and then receive the power and record this voltage as a function of time. So in order to construct an image, we need two dimensions, say x and y. So one of the dimension is generated by your Doppler shift. So we all know about Doppler shift, which is the apparent change in the frequency of received signal because of the function of motion of the target. So one dimension is your Doppler shift, whereas the other dimension is your delay. That means uh, how much uh, how much distant is each point from the radar receiver. I will show some examples how we construct a 2D image from the radar observations we typically carry out. So we typically conduct two kind of observations. One is a continuous wave, in which we transmit just a continuous unmodulated wave, and then we Fourier transform it. So Fourier transform typically we use for taking the time domain into frequency domain and vice versa. So you record the voltages in time, but we divide them as components of frequencies and then inverse Fourier it, so that we can make a time series. And the other experiment is the delay-Doppler imaging, which means we cross-correlate the voltage with the transmitted code. I will show in subsequent slides. So in the first experiment, we typically transmit a signal which is very highly monochromatic, unmodulated. That means it doesn't have any modulation. So we just transmit it and then we receive the unmodulated signal, a continuous wave signal. So typically in planetary radar, we transmit circularly polarized signal because Earth has this ionosphere. In the ionosphere, because of the electron content, the polarization signal is distorted in case of linear polarized signals. So if you transmit a circularly polarized signal, it will be relatively undisturbed with the Earth's ionosphere. So we transmit a circularly polarized signal, typically which lasts about the round trip light time for light to reach and return from the target. And then we received the Doppler shifted echo because the object is in motion. Suppose any planetary object like Mercury and Venus, they always rotate continuously. So because of that rotation, the received signal we observe has a Doppler shift, and that is what we record. So in this way, we do a simple experiment which is called continuous wave experiment. This example shows a Doppler frequency which is plotted against the receiver noise. So in this example, this is a Doppler spectra of an object called 1998 FH12, which is a near-Earth asteroid. So you can see that this limb of this asteroid is moving away. That is why we have negative frequencies. Whereas this limb of this asteroid is coming towards us. That means it is rotating towards us. That is why we see it in positive frequencies. So in this way, we can make Doppler echo spectrums in order to study its rotation. So when we collect all these signals from one object, so we make a Fourier transformation and then we yield a series of time samples, and we can make such kind of Doppler spectrum. So for example, if we observe, so from this spectra, you can calculate the bandwidth, which is I have shown here in this example. So for example, if you observe a 1 Hz of Doppler shift, now this corresponds to a velocity of half of the wavelength per second. Suppose we we use S-band radar wavelength, which is typically at 12.6 centimeter wavelength. So one hedge of Doppler shift corresponds to 6.3 seconds. That means half of this wavelength, 6.3 centimeter per second. So typically we observe, we can measure up to 0.01 hedge. That means we can estimate the rotation of the target, velocity of rotation of the target with a precision finer than 1 millimeter per second. That is the precision we can observe, we can obtain from ground-based planetary observations. Now in the second, so right now we got only one axis, like this curve. This is the Doppler shift experiment. Now in order to get the second dimension, we need to perform a ranging experiment. So in this ranging experiment, we transmit some sort of modulation to the transmitted waveform, because so we all know that modulation is of three kinds. We can do either amplitude modulation or frequency modulation or time modulation, time or phase modulation. So in this case, we do a phase modulation and then transmit a binary code like this, in this like this. So each code has a is comprised of a binary code which repeats in this fashion. So this binary code is selected according to the target we observe. That means each target has a different binary code sequence. So suppose if you transmit the signal and these are the bits, and then when you receive the echo, we actually match that with the transmitted signal. So when there is a positive correlation, we note this as a correlation function. So we apply some sort of autocorrelation functions to match the received wave with the transmitted wave. So accordingly, we can stack all of those received waveforms in according to the time we receive. So this, for example, say this is the signal we received at 0 microsecond, and then for each 1.5 microsecond, we can stack these together and make a time series of those of the recorded signals. So in this direction, we have the time and range, and then we can make a series of these pulses and then stack them into bins. So after you construct this kind of time series, and then we will apply the Fourier transform on the time series to get a spectra for each image like this. And then we line up all of them side by side so that you can make a 2D image like this. So to summarize, in a typical delay-Doppler setup, the incoming radar signal is compared to the transmitted signal. So after comparing, the start of the received signal is identified where the correlation is high. Now the received pulses are all stacked together to produce this kind of time series at each range delay bin. After making this time series, we apply Fourier transform on all those signals. Which gives you the Doppler shift at each point. So the figure on the on the bottom shows how we make a 2D image out of a 3D object. So for example, the planetary object is presented to the radar like this. After making all these delay Doppler processing, what we actually get is this kind of image. So the radar is looking from this direction, from the top, and this green point corresponds to the center of the object. This appears very counterintuitive to our mind, but that is the complex nature of radar images we deal with. So one direction is the Doppler shift. That means it gives the rotation of the target, and the other direction is the range delay. That means this point is closer to the radar compared to this point. So in this way, the delay or range is increasing, and in this direction, the rotation of the object is going on from left to right. So this may appear very complex, but what we actually do is very similar to slicing up a potato and then stitching all of them together to make a 2D image. So this is all about the technique, very brief. I would say very brief because there are so many other things you need to consider. But I'm not showing all of them here because of the time constraint. So let's go to the examples of how we get typical radar images for all the planetary bodies. So let's start with Mercury, because this is the first planet in our solar system. One of the important discoveries from the planetary radar studies is the rotation of the Mercury. That means the rotation period of Mercury has been determined very precisely with radar, and also it was confirmed that Mercury is very weird planet in terms of its revolution around the sun. That means it is in a state of 3:2 spin resonance orbit, which implies that for every 3 rotations of Mercury, it makes 2 revolutions around the sun. That means the length of an year on Mercury is shorter than the day on a Mercury. This makes it very strange planet. This is what we called as 3:2 spin resonance. So this means that Mercury is not synchronously rotating about the sun. This was a discovery in 1965 made using planetary radar. And another important discovery from radar is the presence of water ice at the Mercury poles. So the example I have shown in the bottom, the image on the right. So all of these bright points or bright pixels in the image corresponds to water ice on the poles of Mercury. So the image of south polar region of Mercury. So Mercury has, because of its almost exact orientation with respect to sun, that means it has a tilt angle of less than 1 degree. So there will be some regions which we called as permanently shadowed regions. That means those regions will be in permanent shadow forever. So sunlight never reaches those points. So with the help of radar, we were able to find that such regions can harbor water ice deposits from millions and billions of years. So the plot on the left shows the comparison of Mercury poles with other solar system.
Okay, it seems there is some network issue from his end. Very soon, he will be back with us. So let's wait for a minute or so.
Yeah,
Yes,
seems
yes.
like the network has been disconnected.
There was some network issue probably. So we can
Yeah.
resume. Just it was lost a minute ago. So nothing is lost. I was there. So
Okay.
share your presentation and put it in.
Okay.
Okay. Yeah, I can see that.
Okay.
Okay. Yeah. Okay. Yeah, we were
Yeah. So
talking
this is an
about Mercury.
example.
Yeah. Please continue. Yeah.
Yes. Yes. So I think we have disconnected at this slide.
Yeah.
So this is an example of Mercury we carried out in 2019, that is last year. This GIF image shows observations carried out for over a period of 6 days. You can see how the target Mercury rotates in these 6 days of observations. So the again with all the images, one direction is the Doppler shift, that means the rotation, whereas the other direction is the range, that is the delay of each point from the orbit. So that means radar. That means this point on the top is the closest to the radar, whereas this point, which is the pole, north pole of Mercury, this is the farthest from the radar. So in this way, we can construct a 2D image. Now, let's hop on to Venus. So Venus is a very interesting target for radar because, as I have mentioned before, it is surrounded by huge cloud layers, which makes observations of Venus from optical and thermal infrared observations impossible. We cannot see the surface of Venus with optical cameras. So radar is the first instrument which can penetrate through the clouds and offer the surface views of the planet Venus. This is an example from Arecibo Radar Observatory of the planet Venus. You can see that this is a 5 kilometer resolution image. Again, the X direction gives you the Doppler shift, and the Y direction gives you the range. So these kind of Venus images from Earth-based radar, they have facilitated several spacecraft missions, like from the Russian Venera missions, and NASA had its own Pioneer orbital missions, and recently Magellan mission during the 90s. All these spacecraft missions have benefited greatly from Earth-based radar data. So Venus has been observed since 1964 from both Arecibo as well as Goldstone. So this example shows a Venus image from the 70s. This is a very big, bright target on Venus, which is called Maxwell Montes. It is a volcano. You can see some crater features in this image. The left and right images are different polarization images, so they offer different surface views of the planet. I don't want to go into details of all these images. I will just run through. So this is just to show an example of how you can see Venus from an optical image. This is an example of an optical image taken from NASA's Mariner 10 spacecraft, where you can see only the clouds, huge clouds from the Venus, whereas from radar image, you can clearly see the surface features. So this subset image taken from this global image shows different kinds of volcanic features and several other interesting features, such as these Istar Mons, which is a mountain, and these circular features, craters and coronae and pancake domes. So all these features have been identified using exclusively radar data for Venus. Now, if you talk about Moon, Now, Earth's moon has been studied in very much great detail using Earth-based radars. So, because it's the moon, we also have India also have had two missions so far for the moon, which carried radar instruments on board, both on Chandrayaan 1 and the current orbiting mission Chandrayaan 2. But before that, prior to that, moon has been studied at several different wavelengths, ranging from 3 centimeter to even 7.5 meters, using Earth-based radars. So, because we can only see one face of the moon all the time, that is, the moon is tidally locked to the Earth. From the Earth, we can only see the near side of the moon. We cannot see on the far side of the moon, which is only possible with spacecrafts. So these examples shows uh, the global coverage of moon using radar data from two different wavelengths. The image on the left is taken at 70 centimeter wavelength, whereas the image on the right shows images taken at 12.6 wavelength, 12.6 centimeter, that is S band. So this radar studies of the moon over the years, from even the 60s, proved to be a very powerful tool to study several features on the moon, such as impact craters, volcanic deposits, and the physical properties of the lunar regolith, and several other features, including water ice on the poles. We all of us have seen news that poles of moon contains water ice. So that is a discovery from this is the first discovery implicated from radar observations. This example shows how long wavelength observations of moon from Earth-based radar, that is Arecibo, can reveal so much information when you compare with an optical data here. The image on the left is a visible image camera mosaic taken from the Lunar Reconnaissance Orbiter of NASA, and the image on the right shows a long wavelength, that is 70 centimeter wavelength polarization image of a region called Mare Serenitatis. So you can see these bright features which are buried uh, down the ground up to a depth of 5 to 6 meters into the ground. These are old remnant lava flows and some channels. So these kind of buried features can only be probed by these long wavelength signals. This shows how radar data is complementary to observations carried out at optical and infrared wavelengths. You can see how both the images are strikingly different. As I told before, water ice is a very important aspect that can be studied using the planetary radar observations. There is a phenomenon called coherent backscatter opposition effect, which is thought to be the phenomenon behind the radar scattering from regions that contains water ice. The plot here on the left shows this parameter circular polarization ratio of several different targets such as Europa, Ganymede, and Callisto. These are Jovian satellites, whereas for Mars and Mercury, polar features are up here, and for the moon is up here. This shows that this parameter is very high for regions which have water ice. So this was a result obtained from Earth-based planet radar several decades ago, which was confirmed by spacecraft observations like Galileo of NASA. So even before you send a spacecraft to any planetary body, if you can observe with Earth-based planetary radar systems, you can obtain so much of information, first cut information. The image on the right again shows North Pole of Mercury. So all these images, all these regions which are shaded in yellow, bright yellow, they are candidates of water ice at the North Pole of Mercury. In case of moon, So there are some conflicting results from spacecraft compared to Earth-based radar. In this example, this is the South Pole image of Moon taken from the Arecibo Observatory at S-band, that is 12.6 wavelength. This result implied that the features what we observe are not water ice, but actually they are because of the rough terrain caused by the ejecta of these craters. This is a matter. This is still a matter of debate, which people all over the globe have been trying to solve using variety of techniques, using spacecraft as well as ground-based radar data. So this experiment was carried out in 2005 from Arecibo Observatory. If we move to Mars, Mars is a very elusive target for Arecibo because we don't get opportunities for Mars very often from Earth, from Arecibo radar. So because of the declination limit of Arecibo radar system, Mars can be observed at very long timelines. The next observation from Mars, from Arecibo, is around maybe 30 or 35 years later. So on Mars, there is a layer of dust and soil, the layer of dust across the Martian surface, for which radar is an ideal wavelength remote sensing technique, because these radar waves can penetrate through the dust and then reveal buried terrain. This is a S-band image mosaic of Mars. So this is a collage of several different images stitched together. It's like a panorama of Martian landscape. These covers so many volcanic landforms, such as the Elysium. Amazon is up here. This is the Olympus Mars, which is the highest volcanic peak on the Mars, and Tharsis. So you can, with kind of radar observations, you can study these volcanic features in great detail even before we send a spacecraft up there. So Martian poles also have polar ice caps, just like the Earth has polar ice caps at both the poles. Like we have Arctic and Antarctic regions, the Martian poles also have polar ice caps, and they have seasons also. These kind of features are studied in great detail using Earth-based radar observations, mostly from Arecibo and Goldstone. All these bright features shows different types of ice features. Moving on to asteroids. So radar is a very powerful tool to study near-Earth asteroids as well as main belt asteroids. So near-Earth asteroids are classified in according to their proximity of their closest approach to the sun, and some of them even cross the Earth orbit also. That's why they are called near-Earth asteroids, and they pose a threat to the Earth. Very often we hear in the news that an asteroid is approaching the Earth, whether it will hit the Earth or no. So with radar observations, we can precisely determine its shape, size, its rotation period, and whether it will strike the Earth in near future or not. So radar is our first planetary defense tool. It gives you a very quick estimate of how much distant the asteroid is and what is its next approach, and what all we can do to mitigate its interaction with Earth's atmosphere. So apart from studying all the physical properties, such as 3D shapes, surface features, their spin states, because asteroids rotate, they rotate very fast. There are so many fast rotators as well as slow rotators. You can study their physical properties, such as regolith thickness. You can constrain the composition, and also gravitational environments, because there are so many binary and triple asteroid systems. You can identify them. Radar is a very powerful tool to identify whether an asteroid is a double asteroid or triple asteroid. You can estimate their bulk densities, and you can improve the orbits of their of these objects to a very fine precision. So the curve on the right shows how many asteroids have been detected using mostly the two observatories, that is Arecibo and Goldstone. You can see this curve is updated till March of this year. So you can see that around 930 near-Earth asteroids and 140 main belt asteroids have been studied and characterized using Earth-based radars. Uh, so the red curve gives you like new detections per year, whereas the black curve up here gives you the cumulative total detections. So you can see that these have been carried out from the 70s, and with the increasing capabilities of these radar systems, we were able to get we were able to observe more number of these asteroids, both near Earth and main belt. So I will show some examples of asteroids very quickly. This is an example of binary asteroid. So there is a small satellite rotating this primary body. Like the previous images, again, the x-axis gives you the Doppler shift, that is the rotation. You can see that this orbit is rotating, while the y-axis gives you the delay of this target. This is an asteroid named 2006 BV2. It was observed in 2007. This has been observed uh, monostatically, that means receiving and transmitting at the same station, as well as bistatically, that means you transmit at one place and receive another place. So in terms of its sensitivity, Arecibo radar can detect any 1 kilometer scale asteroids within 0.2 astronomical units. That means it roughly translates up to 80 lunar distances. This is the precision of sensitivity of Arecibo radar system in order to characterize these near-Earth asteroids. These are some of the contact binaries. That means there are some asteroids which have these two different lobes that are joined in the middle, like a contact binary. We call them in general as peanuts because they resemble the peanut shape. So these are the names of these asteroids. These are observed from Arecibo radar system. So we observed that every one binary in asteroid is a contact binary. Roughly 1 in 7 of the binaries are contact binaries. There are some triple systems also, like this famous asteroid Florence. You can see that there is a main body up here, and there are two small moons revolving around this main object. This is the only third near-Earth asteroid system discovered using radar. You can also constrain their sizes. Like this primary is around 4 kilometer diameter, whereas the satellites have around 300 meters diameter. So you can also constrain their rotation, how much velocity, with how much velocity they rotate both the primary body and also the moons. So as I told before, you can obtain very sensitive, very uh, great information from sitting at Earth by observing these solar system objects. So these images are sometimes analogous to images obtained by a spacecraft. For example, this is an object called Tutatis. Now, this is a shape model obtained from radar observations, whereas this is the actual image of that object taken from the Chang'e 2 spacecraft. You can see how exactly they match together. This is another example of an asteroid called Bennu. Some of you might know that there is uh, currently there is a mission going on from NASA, that is OSIRIS-REx. It is sent to observe this object called Bennu. Uh, So this Bennu was observed in 2010 to 2013. So some shape models have been generated using radar observations, and you can see how closely they match with the actual image. This image is taken from the spacecraft. So you can also see that some kind of small features such as these boulders, they even such small features like this boulder, this is also matched in this shape model. So this is the kind of precision we get from Earth-based radar observations of asteroids. Uh, Switching on to comets, radar observations have been proved to be a very powerful tool to observe comets because you can separate the nucleus part from the tail part in radar observations. This is an example of a comet called Iris Araki-Alcock. This is the name of the observers who observed this comet. So when you plot this Doppler spectrum, you can clearly separate the nucleus, which is the solid body, from the tail, that is the coma in the spectrum. Several comets have been observed using radar, mostly from Arecibo and Goldstone. So this example shows the comet Hartley 2, for which a spacecraft mission has been sent. Um the spacecraft mission is the epoxy mission from NASA. You can see how this nucleus of this comet taken from the radar images very closely matches with the spacecraft images. And also radar images for this particular mission helped in navigating the spacecraft, because you need to have a before preview of how the comet looks like, because comets are very elusive in order to target and characterize. It is always continuously moving, and you need to have a preview of the shape of the object in order to reach the comet. Um, so after crossing the comets, radar has been also used to study the Jovian satellites. That means the satellites of Jupiter. In this example, Europa, Ganymede, and Callisto have been observed from both Arecibo and Goldstone. This was conducted in the 90s. So from these observations, it has been observed that all these objects contain huge volumes of water ice, which was again proved later by spacecraft observations, like the Galileo mission. Yeah, so I will pause here for a couple of seconds so that you can guess this object. This was observed by Arecibo radar system in 2005, in 99 to 2005. This, so you can see the rings there, and if you can guess it right, this is Saturn. So Saturn.
Okay, it seems there is some disturbance again. I'm calling him up again, and I request you to wait for a minute so that we can continue. Yeah, so it was disconnected. Just we were talking about Saturn, so we can resume. Just
That is my last slide. Yeah,
okay,
let me
okay.
share the screen. Okay, so yeah, so you can see this peculiar Saturn image of Arecibo.
Please
The entire
share your presentation. We can see, Sriram. We can see the presentation as of now. Just share the screen. Yes, yes, yes. It is added now. Yeah, now it is
okay,
there. We were on that same.
okay,
Yes, continue.
okay. So because Saturn is a huge ball of gas, radar just completely penetrates through Saturn. So the empty space in between the rings is actually where Saturn is present. But because it's a huge ball of gas, you cannot see it from radar images. But you can actually see the rings. So Saturn has several rings with different names. So the names are being names are they are named as per their order of discovery. So in this example, you can see two rings, A ring and B ring, and you can see a peculiar feature here that so the rings are very far apart; they will never cross each other. But you can see that the rings crisscross each other at four different points. This is a very peculiar complex nature of radar images because the A ring is closer to the radar, so it sends the signals back first compared to the B ring. But A ring rotates slower than the innermost B ring. So this because of this different rotation velocity of the outermost ring, uh, so radar records that they both of them are at the same distance, but at same rotational velocity at all these 4 points. That's why you can see these four different types of crisscrossing in the radar images. But this actually doesn't happen actually. They are very far apart. This is one of the examples to show how complex radar images can be. This is very hard to interpret. And I will close by this last slide that the Titan, which is the Saturn's satellite, this has been observed by Arecibo radar in 2003. So this gave you the first evidence that Titan has liquid surfaces. Although the liquid surface, the locations at which the Arecibo has observed doesn't have liquid surfaces, but the first evidence for such hydrocarbon lakes is provided by radar observations, which was later proved by the Cassini-Huygens spacecraft. So these are some of the examples I thought to show in this seminar. And to summarize, these planetary radar observations from Earth have been very useful tools since the 60s. They provide a wealth of data on surface geology of solid solar system bodies. So radar can interact only with solid material. We cannot get any information on objects beyond the frost line of the solar system, that is objects beyond Jupiter. So these radar observations are very important in terms of planetary defense also, because we can observe near earth objects such as asteroids and comets with very high precision. So you can assess the impact hazards, and and these observations nicely complement the astrometry observations obtained from other parts of electromagnetic spectrum, such as optical and thermal infrared rays. Uh, if you want to learn more about this planetary radar, you can use these two links up here. And if you have any questions, you can always write to me. And I will stop here. Over to you, Lalit.
Yeah, thank you so much for this such an interesting session. I really learned a lot from this lecture series. We were talking about different things, and in this one lecture, we have covered a lot of planetary bodies. We talked about
Yes,
how we look at Mars, how we look
from
Venus, and
Mercury to Titan.
yeah, so we covered almost whole of the spectrum, and such a interesting technique. Like when we didn't had technology to go send the spacecrafts and all. So at that time also this was there, and it is always a guiding force for guiding thing. Like
Yes,
we know a lot of information before planning our sessions. So this
yes,
was a really interesting thing, and I'm sure those people who were with us and those who will listen it later will certainly get exposed to this very interesting field, and a lot of people are working there. A lot of things are being done, and the good part is that how you told the how we interpret those images and how we get those images is also a very involved thing. So we generally,
yeah.
those who don't have an understanding, they may think that this is just images and we are talking from there. How we get these images and this process is really involving, and it was really insightful to see all this.
Yeah,
Yeah,
there is
so there are few,
actually a lot of. Okay, go ahead.
yeah. So there are a few questions for discussion. So let us try to take some questions. One is from Ratnesh. Ratnesh is asking, most major of the audience, our audience are university students and new people. So they are asking what is science behind this specific radius. Probably talking about some initial slides when you talk about diameter and radius of these systems. So is it is something
Specific.
related?
I I didn't. I'm trying to understand the question.
Okay,
Specific
means
radius of.
radius of what it is not clear. So probably
Yeah.
I think when you put some initial slides where you're talking about diameters for some radar systems, so maybe he was thinking about that.
It- yeah. It's not clear. It's whether it is about the diameter of radar systems or the objects like
Oh, okay,
solar system
so
objects.
maybe
I'm not sure.
yeah. And then another question is asking what is the speed of signal. So probably all the signals we are using is electromagnetic signals itself.
Yes.
No, so this is
Yes.
the speed of
So we
light.
are using
This is
radar
very
waves, that is electromagnetic waves. So it's just the speed of light.
yeah. So these are some questions from your students, and one thing I would like to ask: we had two sessions before on this series where we discussed
Mm-hmm.
about sun and space weather. So I'm just curious whether this ground-based radar system, uh, how the space weather affects these observations. When we look for the observation, do we need to take care of space weather, and how do it affects? Can
Space
you
weathering.
talk?
Space weathering in terms of what? Because I didn't get the.
Mostly because sun ejects a lot of energetic particles, and so sometimes there are disruptions. Some solar storms are there. Something is there. So
Oh,
does it
we
affect
don't.
our radar
We
observation or
no,
not?
no, no, no. We don't depend upon the sun. We have our own energy. Because
Okay,
radar
okay, okay.
illuminates with
Uh,
its own energy, which is an
yeah.
so that is why we call radar as active remote sensing technique, because we transmit with our own energy and then receive what it comes back. So for example, in optical observations, you entirely depend upon
Mm-hmm.
sun. That's why you
Yeah.
care about the geometry, the sun angle, the illuminating sun angle, where the sun is, whether it is near the zenith or away from the zenith. So such kind of observations are carried out using the reflected energy from the planets, with sun being the source. But for radar,
Mm-hmm.
we illuminate our target with our own radar waves. So we don't actually
Yeah,
depend upon the sun.
yeah. Okay, means when we are sending signal, it doesn't. We don't need to care much about other space weather
No,
conditions. Yeah,
no, and
and
it's like an all it's like an all weather kind of experiment. You
hmm,
can carry radar experiment during sunlight, during nights, during rain, during snow or anything.
yeah. So, remote sensing is recently is being a lot of means it is getting a lot of exposure to new people, the young students from Indian Institute of this remote sensing. They conducted a few outreach activities very widely. So, people are interested, and I hope we will see a lot of young people coming up in the field. And I know that we have a lot of work, a lot of data, and it is when we are talking today, it was planetary bodies, and radar is being used in a lot of other fields. And one interesting,
Yes.
there are few very interesting things you told. One thing about we see generally this asteroid thing, and people are talking that asteroid may come and hit Earth and all. So how what
Yeah.
kind of defense mechanism we have for that? This radar system serves and make tool to alert to tell about things. So that was really interesting. I didn't know it. I didn't knew it before in that way. So that is really interesting thing. And we as you already shared your email, and we are always there. So those people who have something to ask, they can put in comment, and
Yeah.
we will try to resolve it, we will try to answer it. So thank you so much for this very interesting session. And we have almost uh, one and uh, 1 hour and 17 minutes. So it is a good time. And
Yes.
now, since we have conducted 7 lectures in this series, and now I want to announce to our audiences that we are winding up this series, and it has been really wonderful experience meeting with new people, and facilitating an interaction with the people who are doing frontier research, and the people who are looking science as an option, science as a career option. So it has been a really remarkable journey for me, and I have really learned a lot of things in that. So with that, uh, I'm really thankful for all our invited guests in previous sessions and today. And this platform is successful because of the people who are joining us and putting time for us. And these lectures has been really remarkable for the young student, basically, for whom we were targeting. And with this, in the end session, we would like to express sincere gratitude to the chairperson of this lecture series, Professor B.M. Dikshit sir. He's not with us because of some engagements, but his unconditional support and guidance has been a driving force throughout this lecture series. And I express my uh, gratitude for the students and science enthusiasts who have been part of this journey. And I'm sure that they have learned a lot. And at the end of this, we want to share that we are always open to innovative ideas, collaborative learning, and science outreach. So we will plan something, and whatever we do in future, we'll put an that will be. Uh, I have few plans in future to do after this lecture series. The response has been very encouraging. So, with this information, and thanks to all the partners, all the people who have been with us in this journey. And thank you so much, Sriram, for being here with us. And with
Yeah,
that, we are winding
thank
this.
you. Thank you also,
Yeah,
because this is a very good initiative taken by you. Because what I observe generally in our country is that the outreach programs are very at a very bare minimum level. Uh,
yeah,
because
yeah.
a lot of people,
Still, it is.
lot of people at various institutions do a lot of good work, but generally we don't care much about outreach. It is a very important component for all
Yeah, and
others. Like
I'm also thinking like we have a lot of people who have dedicated their life and they have worked wonderful. They have worked out wonderful things. They have given a lot of things to society. So we just don't
yes,
tell people about them. So like in this initiative, we are also trying to take to tell that to offer our gratitude to at least to tell people that there are people who are working day and night for the facilities, for the technical convenience we see today. Our life quality improves because of these scientific adventures and new uh, developments. So it is a really satisfying journey. So thank you. For so we are winding up for today. Thank you so much.